The first part of this unit also dealt with the indefinite integral. And the indefinite integral is when you integrated and said these are all the functions that it could be, so we always added plus c. So you might have gotten used to just thinking, okay, I'm going to just add plus c to everything. But now we get into the definite integral, and the definite integral doesn't have that plus c. And it is definite because we're actually finding a value. Now, I think on your picture, the little yellow, well, they're not yellow, but the little yellow rectangles are actually lined up better than whatever happened on mine. It had a little spasm. So those rectangles were supposed to fit nicely under that curve, and the definite integral has an application to figure out the area under a curve. So if you had a sine or cos curve like this, and you wanted to find the area S, right now we have no technique to find that out. And it's complicated because the shape is curvy. And so an idea would be if we had a bunch of tiny rectangles, that would be a good estimate. And if we kept making those rectangles smaller and smaller and smaller, our estimate would get better and better and better. And so if we took the limit as the number of rectangles goes to infinity, or the base width of each rectangle goes to 0, that limit would approach the area perfectly. And the way that we can calculate that area is by finding the integral between the two values. So here we have an a and a b value saying I want to find the area bounded from a to b under that curve and the positive x-axis. And we can find that by taking the definite integral. That the area will be the integral of that function from a to b. So what does this mean and what does it look like? We're not going to go into theory right now of why it works. But what do we do? Okay, to evaluate the definite integral, we're going to find the indefinite integral just like we've done all the time, but we're not going to worry about adding the plus c, and you'll see why in a second. And I'm going to just call that, when we integrate, I'm going to call that f of x. We're going to write our answer as f of x from a to b. And then to find the area, you just have to plug in b, plug in a, and subtract them. So we can put a box around this. This is the big idea and all the work that we'll need to show. That if you want to find the area under a curve, or the definite integral from a to b of f of x, you integrate, and then you plug in b, and you plug in a, and subtract them, and voila, you have your definite integral. So, let's see, what is my, yeah, and we've got some stuff on our calculator as well. We'll look at some of the calculator stuff in a bit. So we got some definite integrals to start with, but I thought I would just sort of make up, before we get to this one, I thought I would make up an example that would be easy to see. Okay? So if I took y equals 2x plus 1, and 1, oops, that's a little bit off. Whoops, it's really off. Okay. 1, and then here, 2, 3. If we wanted to find this area from 1 to 3, okay, you would know that this goes through the point 1, comma 3, and if I plugged in 3, it's going to go through the point 3, comma 7. Agreed? And if you wanted to find that area, you could do that using the geometry you've had all the way along. For example, I can draw a line straight across here, and that would make a rectangle with a length of 2 and a height of 3. So I would know that the area of this rectangle is 6. And if I wanted to look at this triangle has a base of 2 and a height of 4. Base times height divided by 2, that will get me an area of 4, and I could add those up and say the area between 1 and 3 under the line and the x-axis is going to equal to 10. Now we just had that the area is equal to the integral from 1 to 3 of f of x dx. In other words, the area, according to this new integral idea, is the integral from 1 to 3 of 2x plus 1 dx. How hard is that integral to integrate? Not hard at all. So the next step, what we'll do is we'll write the integral. It'll be, if you want, 2x squared over 2, or you could just write x squared. Add 1 to the exponent and divide, plus x, and we don't write the plus c when we're doing the definite integral, but we write our bounds there that we're still going from 1 to 3. And then we plug in 3, we plug in 1, and we see what happens. If I plug in 3, I'm going to get 9 plus 3. If I plug in 1, I'm going to get 1 plus 1, which will give me 12 minus 2, which also gives me 10, which is the same area that we have. In fact, if we look at these numbers, in this case, the 12 area would have been the area all the way back to 0. So this area, complete area, is 12, and this area right in here, that area is 2. And that 12 minus the 2 gives us the 10 that's left. Okay? Which is kind of neat, because now we could do something we couldn't calculate using our old math, right? This one, with that curve on an x squared graph, we wouldn't be able to figure out that area with any techniques. Probably you could draw a rectangle here and then go, yeah, kind of make a triangle as an estimate or something like that, but it doesn't work out perfectly. Okay, I know that this goes through 1, 2, and 3, 10. But the area from 1 to 3 of x squared plus 1 dx, this is easy again to integrate. And then I always like to draw the brackets with two things like this. Plug in 3, so we're going to get 27 divided by 3, which is 9 plus 3. And plug in 1, which is 1/3 plus 1. So we're going to get 12 minus 1 is 11 minus 1/3. Not 10 to the power of 2/3. 10 and 2/3. That area is 10.7, which is really cool. Because that area, the best we could do before this is do an estimate. And now calculus provides us with relatively easy math, right? There wasn't anything too complicated that we had to do, because we've learned our skills with integration, we've learned our skills with derivatives, and now we have an application that is really neat. Okay? But we're not supposed to do area under the curve yet, but that's just an example. We're supposed to practice the definite integral to begin with. So here's our first example. We want to figure out what the definite integral from 2 to 5 of 3 over x would be. Is yours missing the x? Yes? No? Yours is good? Okay. So first of all, we integrate. And integrating, what is the integral of 3 over x? You recognize it? It's close. This is the tricky one. 3 natural log of x from 2 to 5. Right, because the derivative of ln of x is 1 over x. So being able to recognize that we had a 1 over x first and put it there, and then this will equal this minus this. You plug in 5, 3 natural log of 5 minus 3 natural log of 2. And if you wanted to, you could use your log laws. Whew. You okay with that? What did I do? I brought the 3 in as an exponent. Okay, so that'll give me the 125 and the 8. How did I get the fraction? Subtracting logs is the same as dividing. Good. Oh, there's issues with x's. Does yours have an x on that one? It does. Do you notice in this one that we have a function inside of another function? Okay? When you have a function inside of another function, that's usually a chain rule. And if we're going to do a chain rule, we have to think about integration by substitution, but we only use integration by substitution when you also recognize the derivative present. But the derivative of the inside isn't anywhere. So if you wanted to integrate this one in its current format, if you tried to integrate this one in its current format, it would just be a disaster. Nothing would work. So sometimes we have to do some algebra first. If I multiply this out, are you okay with that? You could draw all the arrows and do it off to the side. Right? But the x times the 1 over x is going to be 1, and that's going to happen twice. Okay? And now we can integrate, so put our square brackets from 2 to 4. This will be x cubed over 3 plus 2x plus, this is x to the minus 2, so adding 1 to that and dividing. Yeah. No, so 1 over x, if you integrate, is the natural log of x, but as soon as you go, you can go back to your power rule. It's only 1 over x that causes the problem. Right? Because if you think about, if I had negative x to the negative 1 and I wanted to find the derivative, I can bring the exponent out in front and subtract 1 from the exponent. My derivative fits to be 1 over x squared. So the power rule only doesn't work when you have a 1 over x or an x to the minus 1. So now we can plug in 4. We get 64 over 3 plus 8 minus 1 over 4. And plug in our 2, 8 over 3 plus 4 minus 1 over 2, and subtract them to get the right answer. Let's pull up our calculator just once to put this in to get this window up, just so you guys get a feeling for how you do that. So we put this in here. So go to y equals, clear out any other equations you have. And we are going to type in the x plus 1 over x squared. X plus 1 over x, oops, all squared. Let's see, what window did we have on our notes? Negative 1 to 20. Yeah, this is fine. Okay, so then second, calculate. Number 7 has the integral. This one we went from 2 to 4, so we can set our lower limit as 2, our upper limit as 4. It shades it under there nicely and calculates the area. That was very fast, a lot quicker than all the math that we did as far as figuring things out. And it gives a very nice visual of what we did. So I'd like you to turn to C, D, E, and F. They are all the same ideas of integration. So the nice thing is the integration part is review for you. Okay? The new thing is plugging things in, and then I will put up the answer so you can see if you're on the right track. Don't worry about the calculation part at the end. Just get the integral and do the initial plugging in. We can copy the correct answers down from here to save us some time. Sometimes there'll be calculator parts to this so that you can find your area under the curve quickly. Then for sure you'd want to use that calculator to do that. All right, so did you integrate correctly? And then plug in your values of one minus the other one. So this is how far you would get up to here without a calculator and be able to leave your answer like that. If you did go to your calculator to get that value, 4.98. Okay. And there's the crazy area under the curve. Just so pretty. It's just unit squared. You don't need that. It's just to show that it is an area, right? So if we're thinking of it as an area, we can write unit squared. Good on this one? Again, don't really need the value there. It's just there for interest's sake. Have you done this one already? No? Oops, there's the answer. Right, you'd have to divide by 3 because there would be a chain rule. Okay? Now, you could have used substitution because the 3x is inside, but you don't need to if it's a simple chain rule, which is just a number, right? Because this one, if you did the derivative, you'd multiply by 3, so when integrating, we think that's going to happen, and so we divide by 3. You need to know your unit circle. Okay, so if you're going from sine back to, again, if I'm doing derivative from sine to cos is positive. Derivative from cos to sine is negative. So if you're working backwards from sine, it would go to the cos one originally, so that's where the negative comes in. What? All that work for nothing? What? What just happened? Why did this happen? Okay, 0 plus 0 is 0. Yeah, pretty confident with that, but at this point, something feels like it's wrong. So let's see graphically what happened that explains this, which is also really cool. This is the graph. And we find out from this one that whenever the area is underneath the x-axis, the integral finds it to be negative. Can you see that if one of those shaded areas was positive and the other one was negative, they would cancel each other out? Okay? And that's what ends up happening in this situation. Interesting, if you type it in your calculator's not quite that smart. See the answer the calculator came up with? Negative 1.07 e to the minus 14. They were close to 0. Algebraic, we know it's exactly 0, but the calculator is always using estimations and getting closer and closer to the right answer. And once it got to decimal 0.00000000000000017, it felt that it was close enough. Right? Just like it sounded like I said 13 zeros there, but you don't know for sure if I did. And you're just assuming that was close enough. Yeah. Homework. Rewatch the video and count the zeros to see if I was accurate or not. Oh no, E's not that bad. I thought it was bad, but the inside's just a 2x, so we can just do the opposite of our power rule and divide by 2 because it would have a simple chain rule. Notice that the numbers go from 3 to 2 instead of 2 to 3. Okay, that's possible. It doesn't make sense with our graph as far as area goes, because our areas are when we go from a lower one to an upper one, but we can still calculate things. We can still follow the rules, plug in our numbers, use our calculator to calculate this, or in this case, we could do it without having to use our calculator to get negative 0.2. So an interesting note that you can write at the end of this one, and I know that you're probably still quite far behind because I'm going fast. But if we wanted to find the area under the curve from 2 to 3, you would get 2/10. And when you switch it to go from 3 to 2, you get the same answer, just the negative value. I'll let you catch up. Now, a little explanation. You know when I showed you the picture earlier today where we had the line and we figured out this area was 10, but our integral said 12 minus 2, and I talked about how this little area was 2, and when we figured out the 12, it figured it all the way back to 0, and then figured this one back to 0 as well, and that gave the 12 minus 2. So if you went with when we did the integral from 1 to 3, it did 12 minus 2. If you did the integral from 3 to 1, can you see that it would do 2 minus 12? And then you get the same answer, because 12 minus 2 obviously is 10. Wow, that's a fancy 10. And that would be negative 10. If you're thinking of it as the area back to 0, which can help you visualize what's happening. All right, 2 more to go, and then we'll get our test back. Oh no, just 1 more to go, and then we get our test back. Our test. Did you integrate correctly? Right? This becomes a plus sign because there would have been a chain rule. You could have showed it as a minus and divide by -1. And then plug in your values. Simplify. Often you would leave your answer in a question like this after simplifying this as -1 minus e squared. If you wanted to get that as a value from your calculator, you could. And just because it is so much fun, oh, I went so fast. Yeah, all right. That's cool. There's the area. It's negative because it's all underneath the curve. So areas above the curve are positive, areas under the curve are negative.